Good afternoon, students. Welcome to physics lecture on third class on oscillation. Today we will discuss about damped oscillation. So I am Dr. Arpan Maiti from PSH Department, University of Engineering and Management, Kolkata. So far, what we have discussed in the last class is that suppose if you disturb a body from its equilibrium position, and then what we will see? Suppose in the case of simple pendulum, I disturb the body from its equilibrium position and then leave it, then due to its elasticity, what happens? It basically vibrates or oscillates, right? And oscillates with its natural frequency. And we have also observed that such a vibration will take place under the influence of its own elastic force, right? And that's why it is called its natural or free vibration. Free means there is no external damping force is present, right? So it vibrates due to its own elastic force, right? So that's why it is known as free vibrations. And we have already solved the equation of motion for free vibration or free oscillation for simple harmonic case y equals a sine omega t plus delta, right? If you remember our last class for free vibration, if you remember the case, we have the solution y equals a sine omega t plus delta. And if you plot this, right? So basically it's sinusoidal curve and its amplitude remains constant, right? Which one is amplitude? This one is amplitude. So with time, so this is my displacement y and this is my time axis. So with time, what we have observed, its amplitude remains constant. That means suppose I have a pendulum, right? And if you vibrate or if you displace the pendulum from its equilibrium position, then what we observe? That it will vibrate or it will oscillate from mean position due to its inertia or due to its influence of its own elastic force, and basically it vibrates its own natural frequency, right? And but what is our practical experience? Our practical experience that it will not oscillate for an infinite time, right? You have observed that after few oscillations, it will stop vibrating, right? So you can ask, sir, why? This is a sinusoidal equation, and why after few oscillations, what we observe in our day-to-day life, after few oscillations, it will stop vibrating, right? If you oscillate a simple pendulum, so after 5 or 6 oscillation, it will gradually decrease its motion, just like this case, right? Just like this case. So why? Because in our day-to-day life that we see, this is not a free vibration. Okay, this is basically a damped oscillation. Why damped? Because you know there is always a resistance, air resistance is present, right? So the oscillator basically loses its energy due to this damping force, right? Like frictional force. So basically, that kind of motion is known as damped vibration. Damped means some kind of damping factor is present. So what kind of damping factor? So for our day-to-day experience, such that frictional force due to air, right? That's why after few oscillations, it will stop vibrating. You see, this is the spring. First, it was oscillating fast, then with time, it's oscillating, its oscillation gradually, amplitude gradually decreases, and ultimately it stop oscillating, right? So that means there is some kind of damping at present. So that's why here oscillation is stopped, right? After few oscillations. So if you see, this is my initial amplitude, right? So this is my initial amplitude. So after few time, you see its amplitude gradually decreases with time. You see, this is my amplitude. So amplitude gradually decreases with time, and ultimately it amplitude becomes zero. So if you plot, so this amplitude basically looks like this, right? So this amplitude basically looks like this. So you see, with time, its amplitude decays with time, right? So, and ultimately the body stops its motion. Okay. So this is known as damped oscillation. Hopefully it is clear to you. So when you can say, when an oscillating body is subjected to frictional force, then its amplitude of oscillation decreases with time, and eventually the body stops its motion, right? So basically that kind of oscillation is known as damped oscillation or damped vibration. Okay. So now what we will do, we will consider, we will try to derive the equation of motion for damped oscillation. So in this case, damped vibration, there are two forces, right, acting on the vibrating body. What are the two forces? First one is basically restoring force, right? And we know what is restoring force is from our simple harmonic oscillation case, right? And we also know that restoring force is basically proportional to displacement, right? We all know it from simple harmonic case. And there is another extra term arises, right, in this damped oscillation. What is that term? That is basically damping force. And this damping force is generally we treat it, it is proportional to velocity of the body. So we can write here two forces acting. So total force is F restoring force plus F damping force. Clear everybody? Now restoring force, which is proportional to displacement, right? So restoring force, what is restoring force? We have already discussed, and we have already know that this is proportional to displacement. So restoring force, we have already discussed so much in our first two lectures regarding restoring force. So it is proportional to displacement. So if restoring is proportional to displacement, and we take this proportional to constant equals and opposite also to the displacement, and we take this proportionality constant as A. So restoring force, we have taken it as minus AX. And damping force, what we have taken? Damping force is proportional to the velocity of the body. So V, damping force is proportional to velocity, and it's also, we have taken the constant as B minus B dx dt, right? Why we have taken minus? Because it is also opposing force, right? So that's why it is negative also. So this is my total force. So we can write what will be my equation of motion? So force from Newton's second law, we can write m d2x dt2, right? Now B is basically known as, what is B? B is basically known as damping coefficient. Damping coefficient. Why damping coefficient? Because its proportionality constant and it arises due to the damping force. That's why we have denoted it as damping coefficient, right? And what is A? A is basically restoring force per unit displacement. This is restoring force per unit displacement. So now this is my equation of motion. So now I can simplify it as d2x dt2 plus b by m dx dt plus a by m x equals 0. Okay. Now we can write it further, d2x dt2 plus, we have taken b by m equals 2k dx dt plus this one as omega square x equals 0. So what we have taken? We have taken 2k equals b by m and omega square equals a by m. Okay. So this is basically equation of motion of damped oscillation. d2x dt2 plus 2k dx dt plus omega square x equals 0 is basically, this represent the equation of motion of damped vibration, for damped vibration. Clear everybody? Hopefully it is clear to all. It's nothing. So what we have included here, for the case of simple harmonic case, that is the only term. For the case of damped oscillation, there is extra term arises due to the damping, and this damping force is proportional to velocity. So that's why v dx dt, and ultimately we have reached to this equation. So this is the differential equation of motion of damped harmonic oscillation, right? Where k, so k, what is my k value? K is basically b by 2m. So as it's come, b is basically come from damping term, so it is known as damping constant. Clear? So k is known as damping constant, that its value is b by 2m, and omega equals root over a by m. Omega, that is equals root over a by m. Okay. So omega equals root over a by m. It's basically known as restoring constant because it arises from restoring force. Restoring force. A is basically constant in restoring force we have taken. That's why omega as restoring constant we have taken. So this is basically known as differential equation of motion for damped vibration. Okay. So next we want to derive this solution of this equation. So how we will derive this? So my differential equation is this one, d2x dt2 plus 2k dx dt plus omega square x equals 0, right? So take this as equation 1. Now this is a second order differential equation. You see, this is a second order differential equation. So let's take a trial solution. Let's take x equals a prime e to the power alpha t. Okay, this is as trial solution. Okay, let's take this is a trial solution. So now put what will be my value of dx dt. So dx dt becomes a prime alpha e to the power alpha t, right? Now a prime e to the power alpha t means x, so I can write it as alpha times x, clear? And d2x dt2, it becomes a prime again alpha, so alpha square e to the power alpha t. So alpha square a prime e to the power alpha t means x, so alpha square x. Okay, now put this value in equation 1, right? Now substituting this value in equation 1, what we will get? So d2x dt2, in place of d2x dt2 we put alpha square x plus 2k, in place of dx dt we put alpha x plus omega square x equals 0. Clear? So x is cancelled, so it becomes alpha square plus 2k alpha plus omega square equals 0. So now alpha, what will be my value of alpha? Minus 2k plus minus root over b square minus 4 AC, A means 1 into omega square by 2. So it becomes minus k plus minus root over k square minus omega square, right? So this is, so there are two roots. These are the two roots. One is alpha 1, that is minus k plus root over k square minus omega square, and another is minus k minus root over k square minus omega square. So what will be my general solutions? Now, so I will put the value of alpha here in the trial solution. Okay, yeah. So general solution will be x equals a prime e to the power alpha t, right? So it becomes, now I put the value of alpha, so it becomes, sorry, so it becomes a e to the power, what is by value of two value of alpha? One is minus k plus root over k square minus omega square. So it is minus k plus root over k square minus omega square times t plus, what is second term? B e to the power minus k minus root over k square minus omega square times t. Okay, because we have received two values of alpha, minus k plus this one minus k minus root over k square minus omega square, and we put these two values here. So a to the power minus k plus root over k square minus omega square t plus b to the power minus k root over k square minus omega square into t. So this is our general solution. Okay, where a and b, where a, b are two arbitrary constant, two arbitrary constant, okay, and can be computed from the initial condition. Okay, now we will discuss three cases. Another is heavy damping, Okay, or overdamping or deadbeat motion. Second one is critical damping, and third one is oscillatory motion. Right. So we will discuss step by step. So first one is heavy damping. Heavy damping means damping is heavy. Heavy over which? Heavy over restoring force. So here damping constant, right? K is basically my damping constant. Here damping constant is much greater than which one? Restoring constant, which is omega. Restoring constant. Clear? So that is the case of heavy damping. When damping, heavy means very high. So which one is high? Damping is constant is high with respect to restoring constant. So there is basically two terms. Okay. Restoring constant, which want to restore to its equilibrium position, and another is damping constant. Now, if damping constant is very high, so what is your general experience? If damping is very high, so it will over omega, so it will not oscillate, right? So it will stop vibrating without oscillating. So we will show this from this general solution. So how? So K is very greater than omega. So what happens then? This term root over k square minus omega square obviously less than k, right? As k is greater than omega, so root over k square minus omega square is obviously less than k. So both the exponents of equation 2, so let's take this as equation 2. So both the exponents of equation 2, it's basically becomes decreasing, right? Is it clear? Because k is higher value than this. So if k is higher value, so e to the power negative term is dominant over positive term because k is high value. So e to the power minus kt is basically dominating over this term. So that's why it becomes decreasing, right? And at t tends to infinity, what happens? This term becomes e to the power minus infinity, right? So x tends to 0. Clear? As it becomes e to the power minus infinity, that becomes tends to 0. Is it clear from this equation? Okay, I am repeating once again. So k is greater than omega. That means this term root over k square minus omega square is obviously less than k because we are subtracting something from this one. So that means k is obviously greater than this term. If k is, so there is two terms. One is minus k and another is this term. And we have seen for this case, k is higher value. So that means negative term, this whole term is negative times t. So as t tends to infinity, so it becomes e to the power minus infinity. That means this term becomes 0. Similar happens to this here also. T tends to infinity. These terms becomes e to the power minus infinity. So it becomes 0. Right? So what that means? It means that the displacement, what is my x? X is my displacement. So it means displacement of the body, displacement of the body gradually decreases, gradually decreases exponentially with time. Clear? So suppose it decreases, right? Its x, its amplitude with time, it decreases exponentially, right? E to the power minus x. Clear? So this is the case of heavy damping or over damping or deadbeat motion. So this type of motion is generally seen. Suppose you have a viscous liquid, right? And you put a pendulum, right? And in a viscous liquid, if you put a pendulum or spring, it will stop oscillating without any vibration. Okay, so that's an example of heavy damping or deadbeat motion, or it's also known as overdamp or deadbeat motion. Another example is of its deadbeat motion is deadbeat galvanometer, right? So it works basically principle of discharge of capacitor through a resistor, deadbeat galvanometer. That is also another example of this heavy damping, overdamping or deadbeat motion. So, let's take suppose another example. So this is my overdamping. You see, so this is my overdamping. So basically, you see, this suppose this is my oscillator, and if I put this in a viscous liquid, so it will stop oscillating without any vibration. You see, its amplitude gradually decreases to 0 with time. So this is the case of overdamping. Next, we will calculate another thing, that is critical damping. That means when K is equals to omega. That means when damping constant is equal to omega, then what happens? We will solve this. So when critical damping happens, when K tends to omega, K is nearly equal to omega, then basically it's known as critical damping. So what is my K? K is basically damping constant and omega is restoring constant. Okay. So when K tends to omega, so what is the mathematical equation becomes? So if you remember the mathematical equation, I am writing again the mathematical equation. X equals A e to the power minus K plus root over K square minus omega square into T plus B e to the power minus K minus root over K square minus omega square into T, right? Now, when K tends to omega, right? So what happens? So before doing that, so let's take this e to the power minus KT out, and okay, for the time being, so e to the power minus KT out, so it becomes A e to the power root over K square minus omega square into T plus B e to the power minus root over K square minus omega square into T. Now we can write this as e to the power minus KT into A e to the power, suppose we take this as B. So it becomes A e to the power beta T plus B e to the power minus beta T. So what is my beta? Beta is root over K square minus omega square. So now K tends to omega. K tends to omega means beta tends to 0, right? If K tends to omega, so my beta tends to 0. So e to the power beta t. So in place of e to the power beta t, I can write a into 1 plus beta t, higher order term I just neglect, plus b into 1 minus beta t. Yeah. So next I can write it at e to the power minus kt into a plus b plus, if I come on b, then b, sorry, if I a plus b, and second is a minus b into beta t, right? Clear? So I can write it as e to the power minus k t p plus qt, right? Where p is a plus b, let, and q is beta into a minus b. So this equation becomes like this. So in the case of critical damping, what happens? The equation becomes like this. So you see, with increasing time, so this is exponentially decreasing term, and t is also multiplied, so it will decay faster. Okay, it will decay much faster than the overdamping case. Okay, so this is the solution for critical damping. So that's why you see, for the case of critical damping, it decays much faster, right? For the case of critical damp motion. So for the case of critically damping, we can write for critically damping case, right? The particle tends to move its equilibrium position much rapidly, much more rapidly than overdamped motion. Why? I have already discussed. You see, so for the case of overdamped motion, only e to the power minus kt, right? This one, e to the power minus e to the power negative time t. Okay, but here we have seen that exponentially decreasing term, and it's with multiplied with t. Okay, so it will decay rather faster than over damping. Okay, so critically damping case, the particle tends to move its equilibrium position much more rapidly than the over damped motion. So this one for critical damping and this one for heavy damping. So particle reaches to its equilibrium position much faster. So at this point it reaches almost zero, but still it is not reaching its displacement towards zero. Okay, so this is the difference between heavy damping and critical damping. Clear? Okay, so next day we will discuss light damping or under damping motion. Light means in this case restoring force is much higher than damping, as restoring constant is omega, sorry, this is restoring constant. As restoring constant is much higher, so basically it will oscillate before stop. Okay, So we will discuss it in the next class. Okay, thank you everybody.